second part of tonight then is to look at algebraic substitution. But just before I look at that, I want to just go back to this question we're looking at, where we want to find this point here, where it crosses over. And if you remember where we got to was, before I decided I'd done enough talking and really needed to do something, was to think about this. Right? Now, at what angle what's the angle whose sine is 0? If we think about the sine function and we sketch it, the sine wave looks like this, and so on. So actually, this is the 0 point here. So there are lots of angles at which the sine is 0. Here, which is the one we identified. If the angle is 0, the sine is 0, but also it happens here, and so on. Okay? There are lots of places where the sine ends up being 0. You might remember, those of you who've done some maths with me before, that one complete cycle, which takes us to here, is 2 pi. And so the point at which it drops to 0 again is pi. So the sine of the angle is 0 at 0 and also pi. And that's the one we're interested in here.
Is that true
Of any sine wave, yes, it drops to 0 at pi. And so we can say that when the sine is 0, when 3x equals pi. So therefore, x equals pi over 3 is the point at which the sine drops to 0. Okay, so the sine is 0 at x equals pi over 3. So going back to the function that this was all about, I want to find the area, if we look at the original integral, between pi over 2 and pi over 3. There's pi over 2. So what is this point? We've just found out. It's pi over 3. So in fact we're okay. In this integral, if I want to find the area between pi and 2 and pi over 3, I'm finding this area. I've not got a crossover where I've got some above and some below. And so that actually turned out to be the limit.
If you've got some above and some below, will it always be equal, or will it actually be
You will end up with the area below subtracted from the area above, which is the example that we were looking at before, where, if you're not careful, we can get a complete cycle where they actually cancel each other out altogether. Yeah, and the answer will be 0. So you just have to watch for this sort of thing where the area might be above or below the limit. And in that case, you need to find this point at which that's the x-axis sometimes. So you can check you're finding the right area. Okay, so that's enough on that for now. What I want to do now is to look at the idea of integration using algebraic substitution. So a new topic. And I want to look at it by way of example. So we're going to look at a few examples of when it's useful. And these examples are taken from the textbook. So if you want to find a relevant section in the textbook, then that will help. So page 465 in the new text, or 442 in the old, you'll find these worked examples that we're going to go over now. So you'll find these worked examples there, and you can look at, but as before, we'll look at the worked examples, and you can see this one, problem number 1 in the chapter, and they go through it. But we'll have a look at it, and maybe we'll do it slightly differently, and then again you can compare the two techniques. Okay, so the standard integral, the idea is to get our problem to look like a standard integral. And that's common abbreviation for standard integral, as we were saying. Standard integral. We've got our table of standard integrals. For this example, we use that the standard integral of cos ax with respect to x is, what's the standard integral for cos? One over a sine ax plus c. So that's the one we're going to use. We want it to look like the cos of ax. That's the one we're going to try and use, where x is the variable and a is a constant. The trouble is, it doesn't exactly look like that. It's the cos of 3x plus 7 with respect to x. So this is not as straightforward. We can't compare it directly with standard integral. Let the bracket, or the 3x plus 7, be u. So it's a bit like this idea of u and v in the differentiation we've been doing. We let 3x plus 7 equal u. So therefore, the integral of the cosine of 3x plus 7 with respect to x becomes the integral of cos u with respect to x. The trouble with this is, cos u looks like a standard integral. The integral of cos u is just sine u. But my problem is that the variable is not u, it's dx. I'm trying to integrate cos of u with respect to x. For this to work, this must be du. So what I do is, I go back to, so to get the integral in terms of du, differentiate u. And rearrange. For du. So u equals 3x plus 7. And du by dx equals 3. So we write down what u is and differentiate it with respect to x, because x is a variable, 3x plus 7. So du by dx equals 3. And then rearrange for dx. Did I say du? Sorry, I meant dx here. What an idiot. Rearrange for dx because I want to substitute in, sorry. So rearrange for dx. Pardon? Because if I differentiate 3x, I'm just left with 3, aren't I? And constants disappear. So rearrange for dx. Dx equals?
Is 7 represent the c?
Yes. Dx equals du over 3. Rearranging for dx. Dx equals u over 3. Treating it like an little algebraic expression. Multiply both sides by dx. And divide both sides by 3 and get dx equals du over 3. It's a bit of a trick because really du and dx aren't algebraic expressions, but we're just changing the variable. Now, instead of dx in the integral, we can write du over 3. Now, the integral becomes integral of cos u times du over 3. So I've changed the thing I'm trying to integrate with respect to the correct form, to u. So I'm integrating cos u with respect to u. That's like 1/3. Du times 1/3. Du over 3 is the same as times by 1/3. So this can become 1/3 of the integral of cos u du. I can take that third outside the integral because it's a constant. Yeah. Because now, oh, yeah, thank you. Cos u du. So now I'm going to do my integration. And this is a standard integral. What's the integral of cos u? Sine u. So the answer is, run out of room, so I'll just... It's sine u, but the number in front of you is just a 1, so it's like sine u over 1, so which is just sine u. So this becomes 1/3 of sine u plus c. Always add that constant of integration. It's not a definite integral, so I need to add that c. Finally, I just replace u with what we set u to be, which is 3x plus 7. So therefore, cos u to sine u, because that's the standard integral. The integral of cos u is sine u. And I'll take the standard integrals. So therefore, we can write the integral of cosine 3x plus 7 with respect to x is 1/3 of sine 3x plus 7 plus c.
Can you just go over the bit where you've done that?
So to review, I want to find the integral of cos 3x plus 7. It's a bit like the chain rule idea. If you think back to that, if we look at this function, the cosine of 3x plus 7, I've got one function inside another. If I wanted to evaluate what the cos of 3x plus 7 was, first of all, I would find out what 3x plus 7 was, and then I'd find the cosine of it. So 3x plus 7 is the inside function, or the one we do first. It's that bit we let equal u. So the idea is we let the 3x plus 7 equal a u, so that then the integral looks like a standard integral. The cos of something equals 1 over a times the sine of something. So if I let 3x plus 7 be u, I can rewrite the integral as cos u. But then I have to change the thing I'm integrating with respect to u. And so to do that, I differentiate whatever I've called u and then rearranged so that it reads dx equals something. And then I can substitute that in, instead of the dx, in here. Oops. In here. Okay, instead of dx, I can write whatever it turns out to be. And when I've done that, I can then do the integral. What's the integral of cos u times du over 3? I can bring the third outside and just do the integral of cos u with respect to u, which is sine u. So the final answer is 1/3 of sine u plus c. And so that's my final solution. Okay.
You're careful this next week.
Yeah. Well, we're going to have a look at another example now. Okay. So just to summarize, I've just written down, no, this in your notes will be what you do to do it, the steps. Let the inner function be u, rewrite the original function using u, differentiate and rearrange for dx, and then use your table of standard integrals to perform the integral, so hopefully it will look like a standard integral at that point. And then in the answer replace u with what it was when you set it. Notes, this technique only works if the original variable disappears, and we'll look at an example there that so you can see what I mean. So I wanted to look at another example and use this technique to do it. So we'll do this one together, and then there's another one that you can work on together, and then I'll leave you with an exercise and we'll call it a night at that point. Okay, so step 1. What was step 1 on that sheet we've just written down? So what am I going to let u be here? Right, let u equal 2x minus 5. Step 1 done. What's step 2? Rewrite the original. So the integral becomes what? U to the power 7 with respect to x. So that's step 2. So let's put these in. That's 1. That's 2. I can't do this integral because I've got u and I'm trying to integrate with respect to x. So what do I do next? Step 3. Differentiate u. So u equals 2x minus 5. So differentiate that. And that's 2. And then I rearrange to give dx. So from this, dx equals du over 2. So step 4. What does step 4 say? Right, so we've got to now do this integral in terms of u. So, and use the table of standard integrals. So we've got the integral of u to the 7, and then instead of dx, I'm going to write du over 2. So now I'm trying to integrate u with respect to u. So that's okay, I can do that. And hopefully now it looks like a standard integral. You don't have to, but at this point I would try and bring this 2 outside, so this can become a half of the integral of u to the 7 with respect to u.
Is that with respect to u over 2?
No, not now, because I brought the 2 outside and called it a half.
Was that?
Yes, du over 2. Just divided by 2, so it's du divided by 2. So I can bring the divided by 2 outside and call it a half. Okay. Now this one's a standard integral. It's the first one in our table. Add 1 to the power, divide by the new power. So it becomes u to the 8 over 8. Plus c. So that's step 4 done. And then the final step, replace u with what we set it to be. And we can also combine the half and the 8, so the 2 times 8 is 16, so this actually becomes 1/16 of u, which is 2x plus 7 to the power 8 plus c.
Why did you use 2x plus 7 also?
Isn't that what we set it to be? Have I made a mistake? Yeah, 2x minus 5. Where did I get 2x plus 7 from? 2x minus 5.
But now if you just kept it as the half, then
Half, no, it wouldn't matter, half and then the 8 underneath, but of course that's a bit untidy because the 2 and the 8 underneath can be combined to 8 to 16. So I would expect to see you doing that. So looking back at our list, at 4, the x disappeared when we substituted back in, and so that's okay, we can do the integral. It might be worth, on this previous page, when we go to step 4, we wrote, didn't we, that use the standard integral table to perform the integral with respect to u. So rearrange for dx. So of course what we could have said after part 3 is substitute this in instead of dx, which is what we did, didn't we? So instead of dx in the integral, we wrote du over 2 in that previous example. So after differentiate u and rearrange for x, then substitute this. Right, have a look at this exercise. If you've got the old textbook, not sure what page it's on, but if you've got the new textbook, can somebody let me know what page number this is on? And then you can have a go at it. So, so in the new text, exercise 184, page 465,